All right, so let's say we have a pipe. And we've got fluid flowing through this pipe. And we want to know, as this fluid flows, how does its pressure change, or what is the pressure inside the pipe? What could we do here to measure the pressure of the pipe? Like if you want to know what's the pressure at, let's say, this location, what could you do, or how could you set it up to measure that pressure? Or how would we usually design this so the pressure is actually displayed somehow?
Well, do we know the velocity?
Let's say we don't know anything about it. We're not to calculate the pressure, but to measure the pressure. How could we build this, like in an actual physical laboratory setting? How could we design this pipe so that we have some way of seeing what the pressure is at that point?
Add a column?
Yeah, if we build a column into this, let's say, if we have a standpipe here, a column, like just this hollow pipe, straight up and down. This standpipe here effectively acts as a pressure gauge. Because the fact that there's a lot, let's say there's high pressure at this point in the flowing pipe, what's going to happen within this standpipe? What would you actually observe here?
It would elevate.
Sorry, what was that?
It would like go high, like into the pipe.
Yeah, fluid is going to rise up in this standpipe because the pressure of the fluid under it is able to support the weight of this column of water. And is the water in the standpipe moving?
No.
So we've got stationary water here versus moving water in the flow pipe. So that means we have to treat these as two separate fluid systems. The stationary water in the standpipe and the moving water in the flow pipe are separate fluid systems. But what we can usually do if we've got separate fluid systems is put a marker at the interface where they meet. So if we just mark the point where they meet, and what's another point where we know the pressure?
The top of the standpipe?
Yeah, at the top of the standpipe, what should the pressure be?
1 atmosphere.
Yeah, or possibly 0 atmospheres, depending on whether you're using gauge pressure or absolute pressure. But whatever we call it, it's the pressure of the atmosphere. And let me label these points. Let me call this, let's say we call the top of the pipe T and the bottom of the pipe B. Even though B is part of the flow pipe, it's also part of the standpipe because it's the interface between the stationary water and the moving water. So if we can use the known pressure at the top to find the pressure at the bottom, that's also the pressure of the flow pipe itself. So the standpipe can be used as a tool to find the pressure in the flowing water. Any questions on that so far? So if we're talking about just that path from top to bottom, what's changing from top to bottom?
The potential energy.
Yeah, we're definitely going to have a potential energy density term, rho g delta y. And what else is changing? Do we need to include anything else?
The pressure is going to be different.
Yeah, you know, the pressure at the top is this low pressure of the atmosphere. Pressure at the bottom is presumably higher pressure. So there's definitely a change in pressure. Is there any change in speed from top to bottom? What do we know about all the water in the standpipe?
It's not moving.
Right. So that means we can ignore speed entirely. There's no change in speed because this entire body of water is not moving. And is there a pump in the standpipe?
No.
So we can ignore that term. There might be a pump somewhere else, but it's not on the path we're talking about from T to B. So we can ignore the pump term. And the pipe may have resistance, but there's no current flowing between T and B. So we can ignore that term as well. So the whole equation just becomes delta pressure plus rho g delta y equals 0. This simplified version of the Bernoulli equation is usually called the hydrostatic case, the hydrostatic Bernoulli equation. Hydrostatic just means fluid is not moving. So in general, anytime you've got a body of fluid where there's no motion and no pump, then you can use this simplified version. But ultimately, it's just from taking the whole thing and ignoring the terms that aren't changing. Which means as we go from T to B, we are decreasing the height and presumably increasing the pressure. We could also fill in some values here. If we write each of these as, let's say, bottom minus top. So pressure at the bottom minus pressure at the top plus density times gravity times height at the bottom minus height at the top equals 0. And we'll probably want to label some of these as well. Let me call that Y actually for consistency. We know the pressure at the top is atmospheric pressure. So I can rewrite that as P atmosphere. Pressure at the bottom is what we're trying to find. And we want to, let's say we put together a labeling system for the heights. What would be a good location to call height 0 as a reference point? If you could choose any location in the standpipe to call height 0, what would be probably the best place to call 0?
B.
Yeah, let's call the bottom height 0. So that'll mean y sub b is 0. And then the top is some distance above that, so some positive height. And we don't really have a number for that, but let's just say it's at height h above the bottom. So let's say h represents the height that water gets to in that standpipe. That means bottom minus top would be 0 minus h. Any questions on that equation so far? So pressure at the bottom minus atmospheric pressure plus density times gravity times 0 minus h would just be negative h. So we get negative rho gh. And then how would you solve that for pressure at the bottom of the pipe? How could you isolate PB there?
Isn't it just rho GH plus pressure, atmospheric pressure?
Yeah, that should do it. So that gives us an overall formula for pressure at the bottom of the standpipe based on the height of the standpipe and of course what material is in it and what planet we're on and the atmospheric pressure. Any questions on that so far? And if we throw some actual numbers in this, first of all, atmospheric pressure, what is the pressure of the atmosphere?
Like pascals or something like
Yeah,
that.
101,300 pascals or 101.3 kilopascals, or rounded off about 100 kilopascals. So realistically, it's 101.3 kilopascals around sea level, but you can usually round that off to about 100 kilopascals if you're just looking for a quick mental calculation. However, that's assuming we're talking about absolute pressure. This is what the actual pressure of the atmosphere is as an absolute pressure. But if we're talking about gauge pressure, what would we treat that as? What does gauge pressure mean? Like if I say this object has a gauge pressure of 5 pascals, what does that actually mean?
Is it like a delta?
Yeah, a delta, specifically the difference between that object's pressure and atmospheric pressure. So if we're looking for the gauge pressure of the atmosphere, that means how different is atmospheric pressure from atmospheric pressure? So what's the difference between atmospheric pressure and itself?
0.
Yeah. So that's the gauge pressure of the atmosphere. If we're talking about gauge pressure, atmospheric pressure is defined as 0 because that's the reference point. Absolute pressure is saying what's the actual real pressure of this object. Gauge pressure is saying how different is this pressure from a reference point we're using. But the atmosphere is the reference point, so its difference from the reference point is 0. This is very much like the difference between Kelvin and Celsius as temperature scales. For instance, let's say we're talking about the freezing point of water. What's the temperature of the freezing point of water in kelvins?
32.
In kelvins?
I mean, 0.
So water freezes at absolute 0, the lowest possible temperature, and no temperature at all?
No, it's 273.
Yeah, 273 kelvins. Kelvins is an absolute temperature. 273 kelvins really means 273 above actual 0. Just like absolute pressure. If we say the absolute pressure is 100 kilopascals, that means 100 kilopascals more pressure than no pressure at all. But if we're talking about Celsius, what's the freezing point of water in Celsius?
0.
0. And 0 degrees Celsius doesn't mean no temperature. 0 degrees Celsius means we're at the reference point, which in this case of Celsius is freezing point of water. If we say the temperature is like 5 degrees Celsius, we are not meaning there's 5 of something. We just mean we're 5 tick marks above the reference point we're calling 0. Or if you have a negative temperature in Celsius, negative 10 degrees Celsius means 10 units below the reference point. Whereas for kelvins, the absolute temperature scale, you cannot have a negative value because you can't be below true 0. Same thing with pressure. You can't be below 0 absolute pressure because 0 absolute pressure means no pressure at all. You can't have less than no pressure. But in gauge pressure, 0 pascals means pressure of the atmosphere. So a negative gauge pressure just means you have lower pressure than the atmosphere around you. Positive gauge pressure means higher pressure than the atmosphere. And 0 as a gauge pressure means pressure of the atmosphere itself. So if you're using gauge pressure, P atmosphere would actually be 0. So if we write this out in both ways, gauge pressure is how different the pressure is from atmospheric pressure. So for instance, if I say the gauge pressure is 20 kilopascals, I mean the pressure of this object is 20 kilopascals more than atmospheric pressure. And the reason that's called gauge pressure is it's what a pressure gauge measures. If you've got it like for instance, a tire pressure gauge, a little machine you attach to the tire and a little stick pops out. The amount the stick pops out doesn't tell you the pressure in the tire. It tells you how much higher the tire's pressure is than the pressure of the air around it. So for instance, if the pressure gauge measures 30 kilopascals, that means 30 kilopascals above and beyond atmospheric pressure. The actual absolute pressure would be that 30 kilopascals plus 101 kilopascals. But if we're talking about pressure as a gauge pressure, we can ignore the plus P atmosphere because that plus P atmosphere is just 0 if we're using gauge pressure as our pressure scale. So as a gauge pressure, we can say pressure at point B is just rho GH because atmospheric pressure is 0. Whereas if we're talking about absolute pressure, pressure B would be rho GH plus 101.3 kilopascals. However, if we're talking about a delta pressure, like let's say we're comparing pressure B with another point further down the line. If you're talking about a delta pressure, let's say pressure 1 minus pressure 2, how would you, like, let's say these are both measured in terms of gauge pressure. How would you convert them both to absolute pressure?
Add 1 atmosphere.
Yeah. Just like if you're converting between Kelvin and Celsius, you'd add or subtract 273 Kelvin. So if we were to add 1 atmosphere to both of these and then subtract, what's going to happen?
You're going from the absolute, or you're going from absolute to gauge.
When we subtract, though, if you got P1 plus 1 atmosphere and you're subtracting P2 plus 1 atmosphere, what happens to those plus 1 atmospheres? If you're taking this quantity, P1 plus 1 atmosphere, minus this quantity, P2 plus 1 atmosphere, what's going to happen when you subtract those?
They like cancel out.
Yeah, the plus 1 atmospheres cancel out, so you still just get P1 minus P2. So it doesn't really matter whether you're using gauge pressure, as long as you're talking about a delta pressure. It doesn't matter whether you're using gauge pressure or absolute pressure, as long as you're consistent about it. Just like if you're talking about a delta temperature, it doesn't matter if you're using Celsius or Kelvin, as long as you're consistent about it. Absolute pressure is like measuring temperature in kelvins. Gauge pressure is like measuring temperature in Celsius, in the sense that gauge pressure is talking about how far are you from a reference point, whereas absolute pressure is talking about what the pressure actually is. But as long as you're talking about delta, you can use whichever one's most convenient, which is usually gauge pressure, because that way you can treat the atmosphere as 0. And that means the gauge pressure at the bottom of the standpipe is just rho GH. In other words, directly proportional to height. Any questions on that so far? So that's ultimately what the standpipe is really for. The purpose of a standpipe like this is the height that the fluid rises in the standpipe directly tells you the gauge pressure at the bottom of the standpipe. Twice as much height would mean twice as much pressure, for example. It's a linear relationship because it's just height times a constant. In fact, if we're on Earth, what's gravity? Value of G on Earth would be how much?
Ten meters per second squared.
Yeah. And what about density? If we're talking about water as the fluid, what would be the density?
I think it's like 1,000 kilograms per centimeter cubed.
Per meter cubed. It's 1 gram per centimeter cubed, but that works out to 1,000 kilograms per meter cubed. And if you combine those, we're going to end up with 1,000 times 10, so 10,000. And if you multiply kilograms per meter cubed times meters per second squared, you end up with pascals per meter. So that means that the pressure at the bottom is equal to the height in meters in the standpipe times 10,000 pascals per meter. And of course, usually we're talking about much smaller heights, usually to be measured in centimeters. So how would you convert between meters and centimeters? What's the conversion factor there? Meters to centimeters.
There's 100 centimeters in 1 meter.
Yeah, so if we divide out 100 we get 100 pascals per centimeter. So if you measure the height in centimeters, you can then just multiply that by 100 pascals. And that tells you the pressure at the bottom. In fact, we can even just mark this if we start labeling the standpipe itself. We could just label the standpipe with tick marks every centimeter. But instead of labeling them as 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, we could label them as 100 pascals, 200 pascals, 300 pascals, 400 pascals, and so on. So if you've got a cylinder that's labeled 100, 200, 300, 400 pascals, you can just look how high the water rises in that cylinder and read the pressure rating right off of that and tick mark. Any questions on that so far? All right, so that's the main idea of standpipes. Next, let's take a look at that example with the 3 cups, which is going to be somewhat similar in some ways and different in other ways. One moment, I will pull that up. Okay, so in this one, we're talking about these 3 upside down cups sealed off at the top, partly immersed in water, and also there's some oil. And if we're comparing locations in these, and ultimately we're just trying to figure out what's the pressure of the air pocket in each one. If we apply the Bernoulli equation here, what would be the only terms we would need in that Bernoulli equation?
Pressure and potential energy.
Yeah, once again, the fluid's not moving and there's no pump. So we can use that simplified hydrostatic version. We can just say delta pressure plus rho g delta y equals 0, the hydrostatic Bernoulli equation. And we can use that to compare any 2 points in this entire system, with the exception that if you wanted to compare any 2 points, what has to be true about those 2 points in order to apply the Bernoulli equation?
Same fluid system.
Yeah, they've got to be the same fluid system. So for example, if we label these, let's say we call these, well, we're talking about pressure of the air. So let's put a mark at the surface between air and water. Because if we can measure the water pressure at the surface, that should be the same as the air pressure at the surface. So let's just call these locations 1, 2, and 3 as labels.
So the pressure at the top of the air pocket is the same as the pressure at the bottom.
In terms of the air itself,
Yeah.
yeah, if we're comparing, like, let's say we call this point 0. If you're comparing points 0 and 1, what's changing?
Potential energy.
Yeah, there is a change in potential energy density. But if you take a look at the potential energy density term, from 0 to 1, there's a difference in height. Earth has gravity. But what do you know about density of air?
It's very low.
Yeah, and since it's such small density, we can ignore that change. The change in pressure from 1 to 0 is so small, it's negligible.
Okay.
In fact, generally for air, for most gases, but really anytime you're talking about pressure of air, potential energy density changes for air don't really matter unless you're talking about very large differences in height. Like for instance, from sea level, if you drive up to the top of the mountain, you're going to notice a pressure difference. You're going to feel your ears popping because that's such a large difference in height. But for small changes in height and talking about a low density substance like air, you don't even need to worry about that difference. It's going to be so small, it's negligible. So we can treat this entire pocket of air as just one single pressure. And that pressure is going to be the same as the water pressure at the surface. So could we compare, for instance, 0.1 and 0.2 directly? Can we draw a path from 1 to 2? Does that pass through only one fluid system?
Yeah.
Yeah, looks like that's just passing through water. and none of the water is moving. This entire body of water is stationary. So this path from 1 to 2 only passes through stationary water, so we're good. And from 1 to 2, ignoring everything else, ignoring the cups, ignoring the water under it, ignoring the air over it, just comparing point 1 and point 2, what's happening to the height?
It's increasing.
Yeah, y is increasing, and therefore what else has to be happening? If delta y is a positive value, then what does that tell you?
Delta P is negative.
Yeah. So that means pressure is decreasing as we go from 1 to 2. Therefore, we know that pressure 2 is less than pressure 1, because if we go from 1 to 2, pressure has decreased. You could also think about this conceptually in terms of the air pocket in cup 1 has to be higher pressure because it's able to push harder on the water, push it further down. So it looks like location 1 is higher pressure air and location 2 is lower pressure air. Any questions on that so far? And can we compare 2 directly to 3?
Well, wouldn't delta Y be 0?
Yeah, there's no difference in height, but what's the problem with the path from 2 to 3?
Oh, there's a different fluid.
Yeah, if we're going from 2 through water, then through oil to 3, that's 2 different fluid systems, so that doesn't work. What we could do instead, though, in general, anytime you've got multiple fluid systems, it's a good idea to just put extra markers, extra labeled locations at any surface where they come together, any interface. So at the interface between oil and water, let's put another mark, and let's just call that location 4. So we may not be able to go from 1 to 3 directly or from 2 to 3 directly, but we can certainly go from 1 to 4 and then from 4 to 3, or from 2 to 4 and then from 4 to 3. And if we go from 1 to 4, what do you notice about point 1 and point 4?
They're the same height.
Yeah, 1 and 4 at the same height. And if they're at the same height, what does that tell you?
They have the same pressure.
Yeah. And note that that's true only because this is hydrostatic. Hydrostatic means we can use this simplified Bernoulli equation where there's just a delta P and a rho G delta Y. So in that simplified Bernoulli equation, if delta Y is 0, then delta P also must be 0. And don't count on that for any system where fluid is moving. If fluid is moving, there's going to be more terms in the equation, so that's no longer valid. But in a hydrostatic system, no change in height is also going to imply no change in pressure. So 1 and 4 are at the same pressure. And then if we go from 4 to 3, that's entirely within oil. So as you go from 4 to 3, what's happening? Would you say the height is increasing or decreasing as we go from 4 to 3?
Increasing.
Yeah, we're going to a higher Y value. So what does that tell you about pressure?
Decreasing.
Yeah, we can go back to the same idea. Y is increasing, so delta Y is a positive value. That means delta pressure must be a negative value. So pressure is decreasing. So we know pressure 3 is lower pressure than pressure 4. But we also know pressure 4 is the same as pressure 1. So it looks like pressure 3 is lower than pressure 1, and pressure 2 is also lower than pressure 1. What does that tell you about pressure 1 compared to the others?
The highest pressure.
Yeah, pressure 1 is the highest pressure. And pressure 2 and pressure 3 are both lower pressure than pressure 1, but we still need to figure out how 2 and 3 compare to each other. Any questions on that so far? So if we want to compare 2 to 3, let's say you go from 2, and of course we'll have to stop at 4 on the way. From 2 to 4, what's happening?
The height is decreasing.
So that means pressure has to be changing oppositely. Pressure is increasing. And then from 4 to 3, we've got the opposite effect. Y is increasing, so pressure is decreasing. So as we go from 2 to 4, we get an increase in pressure and then a decrease in pressure. Are those changes in pressure going to be the same? Are they going to balance out?
Yes.
And how can we tell that they'll be the same?
Because it's at equilibrium, and so that's where it stands. So like the pressure at 4 is going to be the equal and opposite pressure to hold up the oil.
In terms of the changes? Well, if we take a look at those actual
Yeah.
changes, as we go from 2 to 4, we know the pressure is increasing. Can we figure out how much it's increasing by?
We need to know the height.
Yeah. And of course, we don't have a number for that, but let's just assign a variable to that. Let's say the difference in height is, let's just call that h. So let's say this difference in height is h. And note that going from 2 down to 4 is losing height h. Going from 4 up to 3 is gaining height h. So it's the same amount of change in height. We just treat one of them as positive, the other as negative. So if that's height difference h, going from 2 to 4, how much pressure would you be losing? What would be that delta pressure?
Rho GH.
Yeah, rho g h. I guess that'll be negative because it's decreasing. And then what about as you go from 4 to 3? Oh, no, that is a positive. Never mind. We are gaining that much pressure. But what about from 4 to 3? How would you write out how much pressure you're losing?
Negative rho GH.
Yeah. And it's the same height difference and the same gravity. But what do you know about the density as you go from 2 to 4 and the density as you go from 4 to 3?
2 to 4 has higher density.
Yeah, because what material are you going through?
Water.
Right. So that would be density of water versus as you're going from 4 to 3, what are you going through?
Oil.
Yeah. And oil is a lighter density than water, which is why it's able to float. So that means this decrease from 4 to 3 is a small decrease. The increase as we go from 2 to 4 is a large increase. So going from 2 to 4 to 3, you get a large increase and then a small decrease because of the difference in density. So if you got a large increase plus a small decrease, what is that overall?
An increase.
Yeah. And maybe a more moderate increase. So overall, as you go from 2 to 3, you are increasing pressure overall. So pressure 3 is higher pressure than pressure 1. Or sorry, pressure 2. So I think we now know all of the relationships here. Pressure 1 is the highest pressure. Pressure 2 is less than pressure 3 and less than pressure 1 though. So pressure 2 is going to be the lowest pressure. And then pressure 3 is going to be somewhere in between. But it looks like pressure 2 is the lowest pressure. Any questions on that? And in general, keep in mind that the Bernoulli equation is always about comparing 2 points at a time. So if you're dealing with multiple locations, start by choosing a pair of them and compare those, and then another pair and compare those, and keep going until you've figured out all the relationships you need. And always be ready to add in more locations, especially if you've got multiple systems of fluids. Anytime you've got multiple fluid systems, I would just start by marking a location at each surface where they meet and labeling that. You'll probably need that label later on. So may as well just establish it right away. Any other questions on that or any other examples you'd like to take a look at?
So just to so I understand it. So from 2 to 4, it's a large increase because density of water is bigger than oil. So then that's how you know overall it'll be an increase.
Yeah, we've got a large increase because of the high density of water and then a small decrease because of the smaller density of oil. So the large increase outweighs the small decrease, and overall it's a bit of an increase as we go from 2 to 3 in total. Any other questions on that one? Or any other general questions? One other quick thing I'd like to mention about the Bernoulli equation overall. I think one of the most important skills there is knowing when to ignore which pieces. If you've got the entire Bernoulli equation, that's a lot to keep track of. But are there certain circumstances when you could ignore some of these terms? Like for instance, is there any situation where you know there is no difference in pressure? Like if you're comparing 2 locations, is there any situation where you would know for certain those 2 locations cannot have a pressure difference?
Would this be one if you have a cup of water and there's 2 points that are in the exact same level of depth, but there's like no flow of water?
Well, if they're both at the same level, that would really be more about which other term.
Potential energy?
Yeah. So if we split this up, I would say you could ignore this term if both points are at the same height, same altitude, let's say. For pressure, though, if you're talking about hydrostatic, then no change in height also means no change in pressure. But if there's other things that might cause a pressure difference anyway. But are there any circumstances where, like, what would be a common value of pressure where you could say this point has to be at this pressure because of some circumstances? What's a certain pressure that shows up all the time?
If water's exposed to like the atmosphere.
Yeah, if it's just exposed, if it's just open to the atmosphere around it, then you know that that location has to be at atmospheric pressure. And let's say there's another location in the same fluid system that's also open to the atmosphere, then that also has to be at atmospheric pressure. So there's certain circumstances where you know that 2 points must be at the same pressure. For example, if you know they're both exposed to the atmosphere. And there are other situations as well. For instance, maybe they're both attached to pistons that are experiencing the same force. But one of the most common examples is if both of the locations are exposed to the atmosphere. Like one example I see fairly often is if you got like a tank of water that's open on top and also there's a leak at the bottom or a faucet. The leak is a location where the water is exposed to the atmosphere, and the open top is also exposed to the atmosphere. So both the top surface and the leak would be at atmospheric pressure. So if you're comparing those 2 points, there's no delta pressure. Whereas if they're at the same height, you can ignore rho g delta y. When could you ignore the speed term, the kinetic energy density term? When would you know for sure that the two locations have no difference in speed?
When the current coming in equals the current coming out.
For any pipe, we should generally assume the current in equals the current out. But this isn't current, this is speed. Assuming the current is the same throughout the whole pipe, when would you expect that the speed doesn't change either? Or how would you tell if the speed is changing? What's the other important factor that relates speed and current? Yeah, the cross-sectional area. The speed, you should only assume that the speeds are different. If you're talking about two locations in the same single path pipe, the only time the speeds are going to be different from each other is if the cross-sectional area is changing. Like a wider region will have slower speed, a narrower region will have faster speed. But if both points are at the same cross-sectional area, then that means you know there's no difference in speed, regardless of anything else. Pump doesn't matter, resistance doesn't matter, height difference doesn't matter. If the two locations in the pipe are at the same cross-sectional area, they've got to have the same speed. Also, regardless of area, you can also ignore this term if the fluid is not moving. So regardless of the shape of the pipe, if the fluid's not moving, this speed is 0 and this speed is also 0. So that's also no change in speed. So those are good things to watch for. If you know the fluid is not moving, or if both points you're comparing are the same cross-sectional area, you can ignore the kinetic energy density term. If both points you're comparing are the same altitude, even if there's some weird ups and downs in between, if start and finish are the same altitude, you can ignore the rho g delta y term entirely. And then on the other side of the equation, of course, if there's no pump on the path you're talking about, you can ignore the pump term. And if there's no resistance, like if you've got perfectly smooth pipe, which in the real world is not possible, but you can get close to it. If there's little or no resistance, you can ignore IR. But also, of course, if there's no flow, if current is 0, then you can ignore IR. So that's an important skill to have, being able to look at a situation and instead of looking at the entire Bernoulli equation, figure out which terms you can ignore and focus on the ones that are actually changing. Because it's very rare that you need all 5 terms in the Bernoulli equation. Sometimes you do, but usually there are some that aren't changing and you can ignore them. Any other questions on that?
Yeah, I have just one quick clarification. So when we did like the standing pipe, those were like the water in the pipe was different from the current water down like in the lower part because the current was different or the velocity was different. But like
Yeah,
we had to them.
For that one, even though the moving water is touching the stationary water, we still have to treat the moving water and the stationary water as separate fluid systems because one of them is moving and the other one's staying perfectly.
Okay, and we were able to connect like all of this water in this question because like it's all the same, no current.
Right. In this case, the water outside the cups is not moving. All the water is staying still. So everything colored blue in this diagram, all that water is just one big fluid system. The oil would be a separate fluid system, and each pocket of air would be its own separate fluid system as well, because the pockets of air are not connected to each other. But all the water is one unified fluid system.
Okay, and then could you just assume that each pocket of air is 1 atm still?
Not in this case because it's enclosed. It's not exposed to the atmosphere. If you've got like a container that's open at the top, then that has to be 1 atmosphere. But if it's closed, that enclosure could support any amount of pressure. So an enclosed pocket of air does not have to be an atmospheric pressure.
Okay, thank
And that's really one of the biggest differences between these cups versus the standpipe. The standpipe we assume is open at the top, so we have 1 atmosphere as a basis of comparison. But these cups are closed off at the top. They're sealed containers. So that means they do not have to be at 1 atmosphere. They could be at whatever pressure it supports, whatever pressure makes sense under the circumstances. All right, I've got to go get ready for my next workshop, but I will see you next time.